So 1.2 is obviously titled Basic Operations with Fractions. So last section was just basic operations, adding, subtracting, multiplying, and dividing. Last section, that was with just integers, nice numbers and including negatives. This section will be about doing basic operations with fractions. Your most favoritist thing in the world. Or not, who knows. But let's start off with adding and subtracting. So before we start doing actual examples repetitively, let's take a look at this question. Each picture represents what fraction? Do we have a basic enough understanding, foundation of understanding what a fraction is to answer this question? What fraction does this picture represent? And what fraction does this picture represent? Well, tried to give you a little bit of wait time because I guess if you're watching this video, you missed class and all that kind of stuff, but the answer is 1/4. There's 4 sections, equal sections, that this circle, this pie, is divided up into, and 1 out of the 4 is shaded. So likewise, this picture would represent the fraction 2/3. 2 out of the 3 pieces or sections are shaded. So this is like a picture that could represent 1/4, and this is a picture that could represent 2/3. Okay, what do we get if we add these two pictures together? If it helps, it's like what if these were literally pizzas? And you had this much of a pizza, like if you had 1/4 of a pizza, something, a slice this size, and if you had 2/3 of a pizza, basically one giant piece this size, if you add those together, what do you get? Like, what fraction do you get if you do 1/4, or maybe just if you want to think of it as just the pictures? What happens if you add these two pictures together? What do you get? And again, it's like it's no secret now that it's like we're adding 1/4 plus 2/3. How do we add those together? So I'm pausing here to have you just think about it. How do we do 1/4 plus 2/3, even thinking of these pictures, like adding this, basically this shaded slice to this shaded slice, or a couple of slices? Well, to kind of cut to the chase, as they say, adding these two fractions together picture-wise, it becomes a whole lot clearer if you actually slice both pictures up into what? Like how many, once you throw the red lines on there, now what is, like this was fourths, like we cut this pizza up into fourths, and this pizza was cut up into thirds, or the circle, whatever. I mean, you could call it a pizza or not. But so if this is into fourths and this is into thirds, these red lines are now what? Well, they're in twelfths. So now this same shaded area, which is 1/4, is also basically the same as saying what? 1, 2, 3 out of 12. Right? And this picture, which is like, basically 2/3, but when you slice it up into smaller slices, it's out of 12, it's like 1, 2, 3, 4, 5, 6, 7, 8 twelfths. And so isn't it easier to add 3 twelfths and 8 twelfths together, like these 3 pieces of equal size plus these other 8 slices or pieces of equal size? Wouldn't that now be 11 twelfths of a pizza when you add it together? So, I mean, what am I getting at here? Like, the point of this little exercise or discovery thing here at the beginning is basically just to kind of, I don't know, reveal or shine extra, nice spotlight on the fact that in order to add or subtract 2 fractions together, it's a whole lot easier, if the denominators are the same. So if nothing else, like, you probably remember this fact, a lot of you, if not all of you, that in order to, again, this is review from middle school or whatever, that when you add or subtract fractions, at least by hand, the denominators need to be the same. And I hope that this little exercise with these pictures sort of reinforce that or show you like why or what's sort of going on with that. The denominators need to be the same. These pieces need to be the same size. Like, that's essentially what the denominator is. So the denominators need to match, aka these slices need to be the same size. So make sure you finish jotting that down. Pause the video as always if you need. But so let's jump into some examples. So this one says 4/5 minus 1/5. So you can see obviously that the denominators match, which is perfect. So 4/5 minus 1/5, the answer is 3/5. So you go ahead and subtract those, and it's still going to be fifths. And there we go. So 4/5 minus 1/5 is 3/5. How easy was that? Pretty easy, Mr. Falk, right? Next example. Gosh, I'm going to ignore that. You didn't see that. So 1/6 plus 2/3, right? Elephant in the room. These denominators do not match. Okay? You can't really, at least by hand, like add 2/3 to 1/6 if these denominators do not match. Okay? So what we have to do is basically make them match. Kind of like how back here, 1/4 and 3/12 were basically the same fraction. Think about it. If I said, hey, let's take 3/12 and reduce it, you remember that from middle school or elementary school even, I don't know. And your teacher said, hey everyone, what do you get when you reduce 3/12? Well, you get 1/4, because again, like, these two fractions are essentially the same. Just like 8/12 and 2/3 are essentially the same fraction. If you take 8/12 and reduce it, you get 2/3. So we basically sort of got to do the opposite of that, and we have to make these denominators match, right? And here's where we get into a little bit of a can of worms, figuratively speaking, not literally, but we get into a little bit of a can of worms because some teachers, okay, again, like, don't get confused by this, but I think of Mr. Burchanowski, for example, who currently teaches here at Fort LaBeouf. You might know him really well. But something he recommends or emphasizes, right, is to change both of these. If you multiply the 6 and the 3 together, you get 18. So you could basically turn this fraction into an equivalent fraction that was like something out of 18, and you could also take this fraction and change it into an equivalent fraction that was something out of 18. Basically multiplying this denominator by the other one and vice versa. I call it going full birch. I don't know if you ever want to go full birch, but see, I think I tend to kind of lean towards the whole sort of concept or approach of you don't really need to change both of these, because the fact is you could turn 2/3 into something out of 6. You don't actually need to change that one, this first fraction in this particular example. You could turn this denominator of 3 into a 6, and it would then match that one. So how do you do that, right? And again, hopefully by now you've forgotten what's behind this box, but here's what you can do. You can multiply whatever you need to this denominator, right? And in this case, if you multiplied it by 2, it would become a 6. But as this said down here, one of these rules here with fractions that you probably remember from middle school is that whatever you multiply to the denominator, you also have to multiply to the numerator. Them's the rules, because that way the fraction, that's the only way to actually keep 2/3 into basically the same fraction. Of course, it's now like 2 times 2 is 4, and 3 times 2 is 6, just like we need it to be. But so this rule right here that you already knew about from middle school essentially means that 4/6 is going to be essentially the same fraction as 2/3. So whatever you multiply to the denominator to make it match this other one, you also need to multiply to the numerator. So just a little multiplying, that's it, to make, and you do whatever multiplying you need to do to make the denominators match. That's it, And again, you could have multiplied this 3 by 6, and then of course this by 6 to make it 18, but of course this one would have also needed to change to an 18. So again, that's going full birch, multiplying each denominator by the other one to make them match. But again, now that we got this, 1/6 plus 4/6 is 5/6. Okay? So in this one, long story short, we got to do 3/5 minus 1/4. These denominators do not match, so we need to make them match. Okay? Now, as you can see by these boxing here, it looks like we're going to need to multiply something to both the 4 and the 5 to make them match, to make the denominators the same. Do we need to go full birch here? Because look, even when you have to change both denominators, that doesn't mean you always have to go full birch with that. You know what I mean? Sometimes you can avoid multiple, but anyway, what do we got to do here? Like, how can we make these denominators match? Multiplying whatever to 5 can, like if we multiplied 5 by 2, it would make this into a 10. Can we also make a 4 into a 10? No, not cleanly. If we multiply 5 by 3, we could make it into a 15. I don't think we can make a 4 into a 15 to match it. So if we do 5 times 4, we can make it into a 20. can we also make the 4 into a 20 so it matches? Yep. And as it turns out, you probably already, maybe you already went through that quick mental math in your head, of course. But essentially, yeah, you know what? We had to go full birch here. Multiply the 4 by the 5 and 5 by 4, multiply them by each other to make them both 20, right? So you can always do that, go full birch, if worst comes to worst. So 1/4 is the same as, well, what's 1 times 5? 5/20 is the same as 1/4. And if we do 4 times 3, we get 12. And so 12/20 is the exact same fraction as 3/5. And now that we have matching denominators, we can do 12/20 minus 5/20 to make 7/20. And then you are done. Okay. So, this next example, right? Once again, you can tell by the boxes here that, we have to change both because, you can't really multiply something to the 4 to make it into a 6. Like think about it. In theory, could we have left that 6 as 6, like left that denominator as a 6, and only changed the 4 to make it match the 6? Well, maybe technically we could, but not without getting into with super nasty fractions. Never mind. Forget I even brought that up because basically you can't. You can't multiply 4 by something nice, an integer, to make it match a 6, right? So we're going to multiply something to both. And I wish I hadn't just revealed that there on accident. So, to cut to the chase, I guess, what could we multiply to the 6 and the 4? Again, we could, in theory, if worst comes to worst, you can multiply the 6 by 4 and the 4 by 6 and make both denominators 24. But here, again, spoiler alert, I'm really messing this up a little bit today, but in this video. But we don't have to. We don't have to make both denominators 24 because we can make them both what? 12. You can make the 6 into a 12 by timesing it by 2, and you can make 4 into a 12 by multiplying it by what? 3. Okay? So this fraction becomes 2/12, and this fraction becomes 15/12. This is one little teeny tiny example of what I referred to in last lesson as, if you are super comfortable with your times table facts, if you're really good with your mental math, making these decisions, oh my gosh, what can I multiply to 6 and 4 to make them match, or what do I got to do to make these denominators match? If you are not overly reliant on a calculator, then making these quick decisions will come way easier to you. So it's just one little example of what I meant if you heard me say to you, hey, I'll always let you use a calculator, but the stronger you are with mental math, the more times table facts you have memorized, you're going to be at an advantage, and it's just going to be flat out better for you. This is one of those things I was talking about. We can make 6 and 4 into 12, both of them, by doing 4 times 3 and 6 times 2. Boom. And then you get to here, which means now you can add 2 and 15 to make 17. So the final answer here is 17/12. Thank you very much. Ooh, curveball. Little plot twist here in our examples in our lesson. We have to do 3 plus 2/5. How do we take 3, which is just like, I mean, at first glance, not a fraction, and add a fraction to it? What do we do? Little wait time for people at home. Well, here's the thing. You have to realize, so big moment here, if this is something that didn't just pop into your head, like this needs to be something that you can realize on the spot. You can make numbers like 3 into a fraction just like that by writing it as 3 over 1. Okay? Any integer can become a fraction just like that by just putting it over 1. It's a big time weapon that you need to have just real handy. Okay? And now that it's actually looks like a fraction, now we have denominators of 1 and 5, and they don't match, but we can make them match. And this is one of those examples where you can leave 5 alone because you can make 1 into a 5 real easy by doing what? By multiplying by 5. So again, whatever you multiply to the denominator, you also have to multiply to the numerator. That way you're not actually changing the fraction. Some teachers, including me, point out that when you multiply by, I'm getting a little ahead of myself, but when you multiply by 5 over 5, I am getting a little ahead of myself, so I don't know, maybe I'll just stop right there. I'll just, never mind. Maybe I'll bring this up in a later video or a later class. Or later on in this lesson, actually. So stay tuned. But, so whatever you getting back on track here, sorry. So whatever you multiply the denominator, you multiply the numerator. So we got 15/5 plus 2/5, 17/5. Ooh, yeah, talk about a random curveball here. These are what you call mixed numbers. We don't really use a lot of mixed numbers. Like, we don't like to work with mixed numbers in a lot of, like, traditionally in high school. Maybe you did a lot of problems using mixed numbers in middle school and stuff like that, but here in high school, like, we don't really like to work with mixed numbers. At least I don't, and I dare say most math teachers won't. So do you remember how to turn mixed numbers into more traditional fractions, even if it's an improper fraction? Do you remember how to take this mixed number and rewrite it so it's not a mixed number anymore? Do you? Well, here's what you do. The shorthand, quick, like shortcut, whatever, is to do 7 times 2 and then add 3. So this denominator times the whole number, and then you add this numerator. So 7 times 2 is 14, plus 3 is 17, and you just put that over 7. So try that really quick with 1 and 1/4. So 4 times 1 is 4, plus 1 is 5, so you should have got 5/4. So you change this really quick to 17/7 minus 5/4. Now you can move on with it, and denominators don't match. How can I make 4 and 7 match as denominators? Obviously, you got these boxes here because I can't just multiply something to 4 to make it match the 7. So what do you got to do? Well, as it turns out, if you're, again, this is where it helps to be really good with your mental math times table facts, but this is where you got to go full birch, baby. You got to multiply 4 by 7 and 7 by 4. And again, whatever you multiply to the denominator, also got to multiply the numerator. So these fractions become 68. This is something, hey, well, I was going to say, like, even I need to go to a calculator to do this, but actually I could have done this in my head. 4 times 17 is 68, man. And 4 times 7 is 28. And of course, this denominator is also going to be 28. And 5 times 7 is 35. So now that we got, here we go. Let's put me to the challenge here. Not grabbing a calculator. 68 minus 35. I'm going to say that's 33. And I'm right. But hey, no shame whatsoever if you grab a calculator to do 68 minus 35 or 4 times 17. No shame whatsoever. All right, changing gears a little bit. And because now we're going to do multiplying. So when we are multiplying two fractions, 3/5 times 2/7, for example, is it necessary, people, for the denominators to be the same? Do we need to make these denominators match in order to actually multiply these together? The answer is no. Oh, I got to go to my... I'm going to have to get up here and... No, hopefully you can still hear me from like 6 feet away here. So no, the denominators do not need to match. Do we remember the rule here with multiplying fractions? You know, I don't know where you'd have room, whether it's like below this example or to the left of the, I don't know. Wherever you have room, whenever you're multiplying, do we write this down? So somewhere we need to write down, wherever there's room, that when you're multiplying fractions, you multiply across, which means all you got to do is multiply the numerator times the numerator, you know, like 4 times 2, and then 5 times 5. So we multiply across. So 4 times 2 is 8, 5 times 5 is 25, and then always reduce or simplify your answer if possible. Always reduce answer if necessary or if possible. You know, like 8 over 25, that doesn't reduce, so it's done. Okay? And so what I was referring to, I think back here is when you multiply like top and bottom by 5, like here in this example, like where we multiplied the bottom by 5 and the top by 5, it's just like you're multiplying by the fraction 5/5, you know? Like that's technically what you're doing, and it's okay to do this because what's 5/5? What essentially is 5/5? It's 1, you know? And so whenever you multiply something by 1, you're not actually changing it, which that's why it makes it okay. So let me look at this. Multiplying top and bottom by 2, it's like you're multiplying the entire fraction by 2 over 2, which is like multiplying the entire fraction by 1, which that's why 1/6 and 2/12, they're like the same fraction. Because it's like I was multiplying 1/6 by 1. Anyway, so I couldn't leave that loose end loose, untied, whatever. Like I couldn't leave that as a loose end. I had to tie up that loose end. All right, move on for God's sakes. All right. So check it out. 5/6 times 2/3. We don't need the denominators to match, so multiply across. 5 times 2 is, wow. Talk about writing out your work, baby steps. I did not expect that. 5 times 2 is 10, and 6 times 3 is 18. Oh, I know why I wrote it out like that. Because what do I like? So really quick, can 10/18 reduce? Yes, it can. 10/18 reduces to 5/9, right? Yeah. And what I wanted to briefly talk about there is, how should I say this? Some people, like myself from time to time, actually like to do some simplifying, some reducing before you actually multiply. Like, I don't know if you're like me, but I actually noticed that the 6 and the 2 can reduce beforehand, you know what I mean? Which it's really obvious or more obvious when you write it out like that. Like you have the 6 here and the 2 here. And you can do essentially 2/6 and it reduces. Anyway, I don't want to linger on this too much longer. I kind of want to move on. But the bottom line is this. You need to reduce at some point. Whether it's after you multiply, so you get 10/18 and then you reduce, or you can potentially reduce beforehand and then you can do like 5 times 1 and 3 times 3. If you're at all confused or you're just not, I don't know, comfortable doing that, hey, I totally what the heck just happened? Hopefully you're still with me here, because in my classroom